Hi everyone, I'm Sam Liu, and my summer project is on shape anisotropy effects on magnetic domain wall dynamics and spintronic synapses. My home institution is the University of Minnesota Twin Cities, which I just graduated from, and I'm an incoming PhD student at the University of Texas at Austin. I want to thank my sponsors at Sandia National Laboratories and my collaborators Matt, Chris, and Patrick. The main motivator for my project is neural networks, which is a software algorithm that is useful for pattern recognition tasks that humans are traditionally better at, like speech and image recognition. And there's some effort to reproduce this in hardware. So the two main components of a neural network are the neurons and the synapses. So these input neurons essentially take in information from your environment to input into your system. And these output neurons output results that you would base your decision off of. Now the synapses in here are essentially a matrix of weights, and each particular synapse, each particular weight, implements some value between 0 and 1, you can think. Now, the particular synapse we're thinking of is by using a spintronic domain wall device, and more on that later. But our main focus is to be able to modulate the current density versus weight change linearity to be able to optimize neural network training. And making nonlinear behavior happen would help implement unsupervised learning, which is a neural network method that I don't really want to get into, but it's useful for people who do know what neural networks are to know. So I talked about how we want to use magnetic materials to implement these domain wall synapses. And on the left, you can see a linear synapse. And as you can see here, it's a more rectangular shape. So these edges are essentially straight. And you can also see that there are notches, and these notches provide fixed positions and states for the domain wall. And the domain wall is this separation of these two different areas or domains. Now, how these weights are implemented is that the weights are represented by the position of the domain wall. And on the right, you can see a nonlinear synapse. So you can see this slope-like structure here that implements the nonlinearity with respect to current density. So what happens is you use current to drive this domain wall. So you apply current and it drives the domain wall. And here you can see the domain wall moving. To analyze the physics of this system, I'll be using MUMAX-3, which is a micromagnetic simulation software that uses the Landau-Lifshitz-Gilbert equation to solve the magnetization at each time step. Now, the only thing I want to highlight here for the Landau-Lifshitz-Gilbert equation is that the velocity or the torque essentially is linear to the velocity, is also linear to the current density that's passing through the device. After that, I want to be able to produce a SPICE-compatible analytical device model, so I'll be using some one-dimensional analytical equations to do that. And then I want to also put emphasis on ways to minimize leaking behavior in synapses, which I'll describe more about later. To the left, we have a geometry of the system. So we have a trapezoidal synapse where W2 is always larger than or equal to W1 here. And the domain wall moves laterally left and right, and the current is also injected laterally. So the current is injected this way, which means the electrons that provide the torque to the domain wall move this way. Now for the first trial here in the middle, I apply a constant current, and I talked about nonlinear behavior, and this nonlinear behavior can be seen here. So as we can see from the domain wall position, as a function of time, the domain wall moves slower as it gets to the wider areas of the device. So this is desired behavior. So when I talk about leaking as an undesirable behavior, here I apply current pulses at certain time intervals, and in between I have zero current, which allows the domain wall to relax. And when it relaxes, it actually moves. This indicates that it moves backwards across the device, and this is the undesirable behavior I was talking about. So I started investigating other geometries that might minimize this behavior. The first geometry I tried was a synapse with edge roughness. So as you can see here, there's some edge roughness on this picture. For the plot on the left, this is the linearity we're talking about. It's not highly affected. So as you can see, we still get this desirable nonlinear behavior. However, we still see that leaking occurs, just with slightly more randomness. So it's evident that roughness does not necessarily help with domain wall propagation, at least with the leaking portion of it. All right. So this is my second try at a method to prevent leaking. So as you can see here, we have notches on this domain wall that are spaced a certain distance apart from each other and are of a certain diameter and size. So this is semicircular. Now for the nonlinear behavior, we see a little more instability here, but we still get this general nonlinear behavior that we want, which is good. And as you can see here, for the larger notches, we have non-volatility. So as you can see, it remains at its value and doesn't lose its value. So, and my subsequent experiments will be focusing on particularly the notch geometry. So in order to verify that the domain wall pins at each notch, I applied short current pulses and let the domain wall relax into the notch. So from the plot, you can see that the domain wall stops at each notch, like for instance here, 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 and etc. Moving on. The main two observations I want to draw attention to is that from this GIF on the right, top right of the domain wall motion, I'm thinking that the pinning dependence likely depends on Walker breakdown precession of the domain wall. So what does that mean? So as you can see here, this domain wall here is precessing this way, but it's also spinning around. So the magnetization of the domain wall is spinning around. And that's what is called Walker breakdown. So as you can see here, it doesn't jump to the next one for a while, but then it jumps 3 here at each pulse, and it stops again, and then it jumps again here. And so I'm thinking that there might be some dependence on the angle of the domain wall in order to pin. And from here, you can see that at the very last notch right here, it's very hard for the domain wall to pin. So the domain wall likely has a hard time pinning at the edge due to the edge effects of the domain wall interacting with the edge of the device. Now from these micromagnetic simulations, I wanted to develop an analytical model I could use to analyze the device at a multiple device level. So my approach is to use a one-dimensional solution for domain wall motion and Walker breakdown regime. And I want to subsume all geometry-based effects into the field term h. Okay, so what I want to draw attention to is that this v is the velocity of the domain wall in one dimension. And it's proportional to u here. And u is, in turn, linearly dependent on the current density that's passing through the device. And this v is also linearly dependent on h, which here I treat as an effective magnetic field due to the slope and also the notches. So by using a 1D model, here are my fitting results to micromagnetic simulation. As you can see on the left here, the domain wall relaxation for a smooth synapse is quite good, so the fit is quite good. On the right, top right, for the smooth constant current propagation, you can also see the fit is quite good. You can see the nonlinear behavior for the smooth synapse. But the notched constant current propagation was not as good of a fit, so evidently we need to improve our approach for the notch. So instead of having some effective field, it could have some more local effects instead of just a global effective field. Now, the last thing I want to draw attention to is that all of those micromagnetic simulations were done at 0 temperature. And so I also wanted to test what would happen if I introduced a room temperature at 300 Kelvin. So as you can see at 0 Kelvin with notches, the domain wall pins, but at 300 Kelvin, it quickly decays. And so temperature actually has a pretty big impact on whether or not a domain wall will pin. Now this temperature causes random magnetization changes to happen, and as a result, domain wall will begin relaxing and it will depin from the notch. So my next step for this is to see how deep of the notch must be in order to avoid this happening. In conclusion, I set up a micromagnetics model of a trapezoidal synapse using Kofi beam material parameters with an implementation of spin transfer torque, spin Hall effect, Rashba effect, notches and surface roughness, and also perpendicular and in-plane magnetization materials. Notches were identified as a shape-related way to prevent leaking. I also developed an analytical model that's useful for circuit level simulations with the effects of this geometry taken into account through the effective magnetic field term, and also identified some limitations. So the resolution of the device is limited due to notches, the pinning effect is dependent on temperature, and notches in different positions have different thresholds due to Dmag field.